All right, welcome back. So next up is 4.2, using derivatives in applied context. So what's going to happen here is we had talked about the idea of position, velocity, and acceleration and how they apply to our derivatives. So those are not the only types of functions that can apply to a derivative in some way. In general, the units for the derivative, something that we talk about for this, because again, it made sense for the velocity and acceleration, how the units applied there, but just for general problems, if we have f of x has the following units, so it's the units of f over the units of x. If we're talking about the derivative of h of t, it's units of h over units of t, whatever those happen to be. So if f units happen to be, let's say they described f of x as being something in feet, or maybe not feet, let's talk about people, because it's going to be something besides meters per second, all that kind of stuff. And then x was in, let's say houses. Then f prime of x would be people per house. If we had like h of t was described, let's say it's a time unit here. Let's say this is describing it as gallons per second, and then t is obviously in seconds then. So h prime of t would then be based on gallons per second squared. So you have to pay attention to the original units they defined for you for each of these problems if they give you units. So first example, we're just going to be interpreting what these values would mean based off the context they give us. So Mr. Sullivan wants Mr. Brust to finish creating his packets in Algebra 2. Number of packets Mr. Brust has completed is modeled by P of W, where W is measured in weeks. So we want to know what P of 10 equals what is, and also then P prime of 39 is 4. So P of 10 equals 1, so we're talking about 10 weeks. The value of P is 1, so it's going to say it's after 10 weeks, we've completed 1 packet, because they've described for us P of W being the number of packets. Whereas the derivative P prime at 39, the parentheses part is still the week, so we're talking about the 39th week now. The rate though, because now we're talking about a derivative, so the derivative is a rate of this, the rate of 4 packets per week, because again the value is 4. All right, so if we look at this example over here, Mr. Kelly is busy buying baseball cards. So that should just say buying, not busying. Buying baseball cards per year. So that's the rate at which B of t is being modeled as. T is measured in years. So B of 3 is a rate then. So the 150 represents a rate after 3 years. On the third year, Mr. Kelly is buying cards at a rate of 150 cards per year, because they've already described B of t as a rate per year. They didn't say it was cards total, it was rate already. Whereas B prime then is then a derivative of this, so it's based off 10 cards per year is how you'd write it out. You could also write it obviously as 10 cards per year squared. Then perfectly fine. All right, so you do need to make sure you're paying attention to, again, with the number inside the parentheses, it's talking about whatever the unit is there, so that's why it's the 4th year for B prime at 4, 3rd year for B of 3. The 150, the value is what's happening. So this value is based off B of t. B of t is described as baseball cards per year. That's why it's 150 cards per year. Whereas a 10 is based off the derivative, which means we need to increase the unit on the bottom. So that's why it's per year per year. All right, so it's just interpreting these different derivative values. Now, actually solving for different things, well, we have this scenario. People enter an amusement park at a rate given by E of t is 12,500 over t squared minus 32t plus 140. E of t is in people per hour, t is in hours after midnight. Find E prime at 10. Using correct units, interpret the meaning of this value. So we don't want to actually take a derivative by hand. We want to use our n-deriv tool. So when you do n-deriv, you're doing your second math. You're just pressing math, selecting the 8th option, typing this in. Be careful, if you can use your alpha y equals to do your fraction, like it's right now, great. Otherwise, as always, make sure you're properly dividing. So you do 12,500 divided by parentheses, t squared minus 32t plus 140. Anyway, you should be finding your value to be a positive 23.4375. So that's our numerical value. What does this mean? How do we interpret this? Well, E of t is a rate already, so we're taking the derivative, so this is going to tell us that it's positive, and then 10 is implying a certain thing. T is in hours after midnight, so 10 is 10 a.m. So we would say at 10 a.m., the rate at which people enter an amusement park is increasing, because it's a positive value, at a rate of 23.4375. And now for our units, people per hour squared. If you want to write people per hour, perfectly fine. All right, so again, we're using all the information. The 10 is representing as the time after midnight, so that's why it's 10 a.m. E of t is already a rate, but the derivative is referring to a rate, so that's why it's the rate of which people are entering is increasing at this rate here, and we're increasing the time units from hours to hours squared. Very straightforward. So something also to keep in mind, if they wanted to talk about how do I know if the amount of people in the park is increasing or decreasing, I wouldn't need a derivative. The derivative represents the rate at which the increase or decrease is occurring. The original increase or decrease is just based off an original rate, so it would only need E of 10, not E prime at 10. Local pizzeria opens at 9 a.m. The number of people in the pizzeria can be modeled by P of t. It's this lovely function over the interval from 0 to 10. T is measured in hours. 9 a.m. corresponds to t equals 0 when they open. The number of people in the pizzeria increasing or decreasing at 3 p.m. So 3 p.m. is 6 hours later, so we want to talk about when t is 6. So the question is, do we want p of 6 or do we want p prime at 6? So it's all about whether or not p of t is an actual rate or is it just a number of people. So they tell us the number of people is modeled by p of t, so this would be people at 3 p.m., how many people are in there, where this would be the rate of people per hour. So we want p prime at 6 then. Because we want to know whether we're increasing or decreasing, we want to know what is the value of the derivative, what is this rate occurring at. So p prime at 6, again, don't do the derivative by hand, it's a funky product rule. Everything else, do your end deriv tool. You'll find you can get 44.3539. So very simple, explain your reasoning. Since p prime at 6 is well, it's actually right there. You can actually see what I wrote. That was messy. P prime at 6 is positive. The number of people in the pizzeria is increasing. All right, very straightforward. Now let's do one more scenario with using this kind of concept. So this one, we're talking about crocodile population in Florida, modeled by the differentiable function c of t. So c of t is the population of crocodile from 0 to 50. T is measured in years. There are currently 50,000 crocodiles in Florida at t equals 0. The birth rate for crocodiles is modeled by b of t, which is this 2,000 e to the 0.07 t crocodiles per year. Death rate is modeled by d of t, 240 e to the 0.15 t crocodiles per year. Is the crocodile population increasing or decreasing at t equals 6? Explain your answer. And is this rate of change in the population increasing or decreasing? Okay, so we want to set up what c of t represents. So c of t would just simply be b of t minus d of t. Birth minus death. That tells us the population. Technically, we would also include that 50,000 if we want to talk about how many crocodiles are actually in there, but that wouldn't be c of t. That would be based more on going backwards, because b of t and d of t are both actual rates. They're crocodiles per year, not crocodiles. So 50,000 is not relevant to this particular scenario right now, which means we're not actually taking a derivative to find c of 6. We're just doing b of 6 minus d of 6. So however you best want to type that into your calculator, doing it all at once or however you want to do it, but you were going to type in the 2,000 e to the 0.07 times 6. That's the exponent, and then 240 e to the 0.15 times 6, and you're going to get a value of 2,453.6184, which means the crocodile population is increasing. So our croc population is increasing. Now, is this rate of change increasing or decreasing over time? Because it's entirely possible that you could have something that's increasing in value, but the rate of increase is slowing down. This is best described by a curve that looks like this. you can see that curve is still increasing the whole way, but it went from a sharp slope to a flatter slope. So that would be a scenario where we are increasing at a decreasing rate. Whereas, so this would be increasing at a decreasing rate. Whereas a graph like this would be increasing at an increasing rate. So that's what the second part of this question is asking us. Is the rate of change in this population increasing or decreasing? Well, since we want to talk about what's changing, now we're referring to the derivative. So C prime of t would be B of t minus D of t. B prime of t. So we want to know what's happening at 6. So we're doing the derivative of b at 6 minus derivative of d at 6. Now for both these, again, you could do it by hand or, again, use your n-deriv tool. So if we use your n-deriv tool, you'll get a positive 124.5289, which tells us that the croc population is increasing at an increasing rate. So it's going to be more like this scenario right here rather than the other scenario. All right, so the biggest things you really just have to watch out for with these rates of change is the units and the context, and whether or not you need to take a derivative like we did really for 3 and 4, or you leave it alone like we did here for the first part of the question for number 5. Just really look at the information they give you. Is it a rate by itself? And what are they asking about, increasing or decreasing? So, because again, the first part says, is the crocodile population increasing? So we're looking at the derivative of the crocodile population. That is already represented by B of t and D of t. Whereas the rate of change of the population, now we're looking at how that is changing. So now we're looking at the derivative of those derivatives. All right, so that's just, again, a couple of applications of these derivatives that are not related to position, velocity, and acceleration. You can still apply all the stuff we just did here to position, velocity, and acceleration as well. All right, next up is related rates. This is talk about how things are changing with respect to time. So we're going to start taking derivatives with respect to different variables besides x. Technically, we're kind of doing that here. The b prime of t, d prime of t was based off respect to time. We're going to look at that in more algebraic sense. All right, so I'll see you next time with that video.